think I'll be live in few seconds on YouTube. Let's see. Let me put the link out on Twitter. Let's see. Live now. Join in. Okay, so as I said yesterday, let's try to write some code. Hopefully, open. Cool. We have this file. Can you see this? Yeah, you can. We saw this interaction. Now we need to again we need to check this again and again till we get the complete idea. So this returns signal single signature. Yeah, this returns single signature. This this aggregates the signature, and this verifies the signature. So that's the and we had that. Let me find it. Just a second. Yeah, we had this repo where this guy was showing us closes. This guy had these two functions, validate signature and validate signature and aggregate signature. So for aggregation, it's BLS helper lib BLS helper struct sum go back. It's validates signature and it aggregates the signature, but we don't have what we, but we don't have the create single signature which this should return. This contract should return. So that's where we have the issue. This aggregates, this checks, verifies. 64. Okay. Then decode signature. We know in the aggregate signature we already saw it returns sig sum x dot sum y. So this is using helper. Sum this sum of all points on in the array. BLS open verify single verify multiple hash to point is BLS key. What is this message? I guess here we are generating the what was that? Safe. It needs three values, right? Right. I remember seeing that somewhere. It had three values. Okay, public key, the message, and the signature. So yeah, you see here this one I was saying verify multiple. Are you doing this here? Aggregate. Okay, domain. We found the domain. This is the domain. Then this is the some constant. Ithaka BLS GitHub Odyssey examples. This is the one BLS multisig. Oh no, in the contracts we have the libraries which is BLS. Should we read this for BLS signatures? EIP 2537. EIP 2537 BLS precompile compile for BLS 12 381 curve operation adds operation on BLS curve as precompile and set in a set necessary to efficiently perform operations such as BLS signature verification. Add a functionality to efficiently perform operations over the BLS curve, including those for BLS signature verification. What BLS generate a signature? Intro to BLS. curve programming ECC. Okay, this one. Ben Benjaminian. Okay, the username is cool. Uh, okay, we have Ben here who has written this for us, the the dumb people, at least me. So this whole stream will be reading this and understanding how the fuck this works. If not, I already have this part which just tells by string coincidence in addition to signature scheme. The acronym BLS sometimes refers to a way find elliptical curves used in pairing based cryptography. I think R will be pairing based cryptography. Okay, let's read this because this is actually related to what we want to do. We're gonna use the Odyssey testnet with Foundry. Odyssey testnet? No, but like there is inbuilt. Just a second. There is inbuilt functions that we have, and we can use those. So hash 2 point G2. What these things are like FP G1, FP2, G2. I need to understand all of those, and I'll will understand this here. BLS 12-381 for rest of us. Everything I wish I knew before I started fiddling with this thing. Thank you. I should have read this ages ago. The elliptical curve BLS 12381 has become something of a celebrity in recent years. Many protocols are putting it to use for digital signatures and zero knowledge proofs. Zcash, Ethereum 2.0, Scale, Algorand, Definity, Chia, and more. Unfortunately, existing materials about BLS 12381 is fully obscure. Incantations is full of obscure incantations like inst- instantiating, instant, instantiating, instantiating. It's access twist. Okay, and optimal extension field tower. I'm here to fix that. I won't be okay. Let me put this in the chat because that's where you guys can check it out. BLS for rest of us. Okay, link is in the chat. You guys can hopefully see it. If not, put it in the chat and I'll send it again. I won't give a general introduction to elliptical curves and their exciting group properties. There are already some great primers. We should read this. Gentle introduction. That's cool. Covered in this. Next. Okay. So I think we we can do this also. This is much. Right now we'll read this, but afterwards we can read this part where they are explaining elliptical curves. So basically ECDSA, yeah, ECDSA, ECC, whatever. We have heard of these things before in our programming, like in our account abstraction examples only, where we were doing this signature verification and we were using ECDSA. We just know the parts, like w- how to use it, but not what it does exactly. Okay, let's go over this. No, this. Yeah, I won't be giving a general introduction to elliptical curves and their exciting group properties. There are already some great primers out there, and I will assume basic knowledge of these things equally. These things equally. There is much in here that is not specific to BLS 12381 and applies to other curves. Motivation: BLS 12 BLS 12381 is pairing friendly elliptical curves. Pairing based cryptography has developed over the last couple of decades, application enabling useful new applications such as short digital signatures that are effectively aggregatable, identity based cryptography, single round multi party key exchange, and efficient polynomial commitments such as K, KZ, KZG commitments. Z, ZG? Okay, I can't pronounce that quickly. Pairing friendly elliptical curves. Let me zoom in. Okay, pairing friendly elliptical curves are curves with both a favorable embedding degree, uh, to be explained below. Okay, and large prime order subgroup also. Okay, these are rare. If you create an elliptical curve at random, it has minuscule chances of being pairing friendly. However, they can be constructed, and BLS curves are explicitly constructed to be pairing friendly. Several other families of pairing friendly curves are also known. What what are those other curves? Okay, no, there is no chance I can understand any of this. So we can ignore it. Not ignore it, but I'll read it afterwards. This is much important because I want to understand what is BLS, how BLS signatures work. I have done ECDSA, like verification of ECDSA signature and how to use those, because there are a lot of tutorials, and also I did that and on Cypher, so it was much easier for me to understand. But BLS is not that much. Okay, next, some good some good reading if you want to learn more about pairing based cryptography. A short but technical explainer, and another one, Vitalik with Vitalik with a great general introduction to elliptical curve pairings. This NIST report is quite readable. I recommend section 2 and the appendix. Okay. We have a lot of reading here. You see, these primers, I said, then these explainers, we can also check this. This would be much more interesting because Vitalik wrote it. Also, good background is draft IETF standard for pairing friendly curves. If you really want to understand this stuff, then pairing for beginners is awesome. Let's check that too. Pairing for beginners. Oh, this is Hola's book. This is not a single article, but I'll just download this and I'm gonna read it afterwards. Not on the stream because it will take few days. Right now, oh, where? Yes, here. Pairing for beginners is awesome. It turns out to be a lot less scary than it looks if you work through it carefully, studying the examples as you go. I really recommend this. I'm perpetually halfway through it. Okay, about curve BLS. Just a second. Oh, lot of people joined. Four. That's the highest number since I started streaming. But yeah, hello guys. Hopefully you'll be here for the whole stream. If not, I'll be sad, but it's okay. Okay, history curve BLS 12 381 was designed by Sean Sean Sean, who knows, in early 2017 as the foundation for an upgrade to Zcash protocol. It is both pairing friendly, making it efficient for digital signatures and effective for constructing zk snarks. Okay, a proliferation of new generation scalable blockchain protocols has put a premium on generating short signatures that can be efficiently aggregated or easily thresholded. The properties of BLS 12381 frequently makes it the curve of choice for these protocols. Several cryptographic libraries, established one established ones such as Apache Milagro and emerging ones such as Hirumi and BLST supports BLS 12381, and there are already moves to include BLS 381 in some standard such as pairing friendly curves, hashing to elliptical curves, and BLS signatures. This is good news for protocol interoperability. Cool. Naming BLS 12381 is part of family of curves described by Bar- Barreto, Len, and Scott. They are the BLS in the view here. The different BLS trio will appear later. Okay, the the 12 is embedding degree of curves, neither too low nor too high. We'll discuss embeddings in a little while. The 381 is the number of bits needed to represent coordinates on the curve. The field modulus q, the coordinates of a point come from a finite field that has a prime order, and that prime number q is 381 bits wide. 381 is fairly handy number as we can use 48 bytes per field element with 3 bytes left over for useful flags or arithmetic optimization. Arithmetic optimizations. This size of this size this size of this number is guided both by security requirements and implementation efficiency. What are the security requirements? Oh, this is just different section in the same article, so we'll read that afterwards. Curve equation and parameters. The basic equation of BLS 12381 curve is y square equal to x cube plus 4. Should we have like create graph online? From formula graphing calculator y, where is y square equal to x cube plus 4. Yeah, oh no, let me reset it. Yes, you can see this is a curve. This is how it looks. The key parameters of a BLS curve are set using single parameter x, different from the x in the curve equation, that can be selected to give the curve nice properties for implementation. BLS 12381 is derived from the k equal to, what is this? K equal to 0 mod 6. Case of construction 6.6 in the taxonomy. Specific design goals of BLS 12381 are X X has low Hamming weight, meaning that it has very few bytes to set a 1. This is particularly important for efficiency algorithm that calculates pairing, the Myler loop. The field modulus Q mentioned above is prime and has 383 bytes or fewer, which means 64-bit or 32-bit arithmetic on it, which makes 64-bit and 32-bit arithmetic on it more efficient. The order R of subgraph, which order order R of subgraph we use is prime and has 255 bytes or fewer, which is good for the same reason as above. The security target is 128-bit. See below. Okay, we'll read the security level. To support ZK snark schemes, we want to have large power of 2 root of unity in the field fr, which means we want 2 raised to n to be factor of r minus 1 for some biggish n. Make x a making x a multiple of 2 raised to n by 2 will achieve this. Okay, this property is key to being able to use fat Fourier transforms for interesting things like polynomial multiplication. The x equal to 0, I don't, hexadecimal value, note that it is negative, gives the largest q and the lowest Hamming weight meeting these criteria. With this value, we have field modulus q, subgroup size r, and then the hexadecimal values for both 381 bit prime and 255 bit prime. Understood? Reference for much of this section. Lots of curve data is also an IETF specification. Field extensions. Field extensions. Field extensions are fundamental to elliptical curves. The 12 is the 12 in is BLS 12381 is not. I think here it should be the 12 in BLS 12381 is not only embedding degree. They should be in, not is. But okay, he's more like smarter than me, so maybe just mistake. It is also the degree of field extension that will need to use. The field FQ can be thought of as just the integer modulo q 0 1 to q minus 1. But what kind of beast is fq fq raised to 12, the 12th extension of fq? I totally failed to find straightforward explainers for field extension out there, so here is my attempt after wrestling with this for a while. Let's construct an fq square. The quadratic extension of fq in fq the quadratic extension of fq in fq square will represent the field elements as first degree polynomial like a0 plus a0x, a0 plus a1x, which we can write more concisely a0 a1 if we wish. Adding two elements is easy. a comma b plus c comma d equal to a plus bx plus c plus dx equal to a plus c in brackets plus in brackets b plus d into x. We just need to be sure to reduce a plus c and b plus d modulo q. No idea what they're doing. Oops, what we were supposed to do with that x raised to x square coefficient. We need rule for reducing polynomials so that they have a degree less than 2. In this example, we're going to take x square plus 1 equal to 0 as our rule. We need to make sure other choices there, but we sorry as our rule, but we could make other choices. There are only two rules above that rule. It must be degree k polynomial, where k is our extension degree 2 in this case, and it must be irreducible in the field where we are extending. That means it must not be possible to factor it into two or more lower degree polynomials. Okay, applying our rule by substituting x square equal to minus 1 gives us the following result. Last, you can see AC minus BD comma AD plus BC. This might look a little familiar for complex arithmetic. This is not coincidence. The complex numbers are quadratic extensions of real numbers. Cool. Okay, I don't understand yet here. Sorry to curse, but I really don't. Using VLSI. Okay. This section is miscellany. Okay. Of things relevant to BLS signature. Okay, that's cool. That's what we want. BLS 12, BLS digital signatures. Now that it's time to introduce other BLS, bone line, bone len, and Techum. The L is same as BLS 12381. The B and S are different. Okay, BLS signatures are introduced back in 2001, a little before BLS curve family was published in 2002. But pleasingly, they go hand in hand. BLS signatures can use other curves. BLS curves has uses other than signatures, but but it's nice when they come together. There is a pretty concise but lucid description of BLS signature scheme in the draft IETF standard, also GitHub repo. I will check that. Private public keys. The private key to be used for signing is randomly chosen number between 1 and r minus 1 inclusive. We'll call it SK. The corresponding public key, if we are using G1 for public key and PK equal to SKG1, where G1 is chosen generator of capital G1, that is G1 multiplied by SK, which is G1 added itself SK times. Discrete logarithm problem means that it is unfeasible to recover SK when given public key PK. Signing. To sign a message M, we first need to map M onto a point in group G2, where we are using G2 for signatures. See hashing. see hashing to curve below for a discussion on ways to do this. Anyway, let's assume we can do this and call the resulting G2 point HM. We sign message by calculating the signature. What is this? I don't remember what that symbol is called. I forgot. Oh, sigma. Cool. Sigma equal to sk. Sigma equal to this equation. That is by multiplying the hash point by our secret key. Verification. Just a second. Huh? Okay, it says it is for practical use, but it's not. It's just more text over text over text. Okay, you guys have the link, so please check it. I'm gonna read it after the stream. And yeah, gonna read this gentle intro also. Let me put it again in the chat. Gentle intro to ECC. I have sent this link too, so you guys can read it. Also, maybe do a refresher on algebra to understand what they're saying, because I completely forgot what Fourier's theorem is, like Fourier transform is. I have learned it in electrical, but I don't remember what Fourier transform is right now. So I have to do a refresher on that too. Maybe I can do one stream where I actually like write down the things and explain the mathematics. But today is not that day. Okay, cool. Uh, I'll end the stream early. Also, from tomorrow onwards, we are not gonna spend any time on this. We are just gonna keep that where it is, and we're gonna move on to something new because this is taking too long. I don't have any point of references, so maybe we should put it aside and move on to new chapter on the live streams. Maybe Nil this one. I know Nil dot foundation. So this project, or I want to explore the other one, which is fluent.xyz. Yes, fluent.xyz docs. Both are great. Or what we can do is we can build a liquid staking application on C. That's also good because I have worked with C.io. That's the name. C.io and developer docs. Okay, so in C, you go here, EVM precompile and staking and staking. Yes. So this precompile allows you to access their staking functions, and with this we can actually write a good write a liquid staking application for C, and it will be pretty interesting for us to write. So we have three options, 1, 2, and 3. So I don't know what you guys want to do. if you want to have it, if you want to do whatever, like if someone else is watching, like you guys, you can tell me, say fluent or nil, what's more interesting. Here we can build actual, like useful real world application. Real world in the sense, I know how to build it. Here we can explore fluent, and nil foundation I have already worked with it, so I know how to use it. So we have three options: 1, 2, and 3. Whatever we want to do, I'll just like do a coin toss, or choose one out of three. Three online. Random number generator 2. Fluent. Oh no. 1, 2, and 3, right? Liquid staking. Cool. Okay, let's line them up. 1, 2, 3. Can we roll? 1. Fluent. Okay. Tomorrow we are checking out Fluent and trying to understand understand how Fluent works. You can you can go to this anytime, but we'll do something. Try to write a hello world application and do something different. Blended apps. Yeah, that's the plan. Okay, cool. We'll try to deploy the this application, like Fluent application, on mainnet. Sorry, testnet tomorrow, or devnet, whatever you want to call this. And just intro to Fluent. What after that? What you do? Okay, this is ridiculous. That okay. Now we can stop and see. First, first Fluent, then nil, and then say. That's what we'll do. So tomorrow we'll check out Fluent and just start mm, exploring it. How to create these blended apps. The idea they have is you can put multiple VMs into one, and that's how they get this blended application. Composability between different languages and different VMs. So that's what we want to explore tomorrow. Cool. I hope you are excited for that. This would be more hands-on than today's stream, where we just read theory. But for now, we are putting the BLS part of account abstraction on ice, and we'll come back to that later, maybe few weeks down the line. But I want to write more code on stream. So tomorrow, Fluent. That's the target. Cool. I hope you like the stream. Probably not. I also didn't like today's stream, so I can't blame you. But hopefully you'll like tomorrow's stream, and looking forward to having you here. Have a nice day. Bye.